Okay, on this page here I have the outline of the notes that you need to know. Just quickly going through some of them, if I can get my thing. We had the very beginning of the evolution of the atom started with Democritus, who was a Greek philosopher, and he termed the word atom out of the Greek word atomos, which meant the smallest particle of matter. And then, as you'll see as we progress through this video, I'll talk more about Dalton and Dalton's postulates. Then we talk about J.J. Thomson and Thomson's plum pudding model. We have to make note of Rutherford and his contributions and Rutherford's model with the gold foil experiment. Then we had Niels Bohr and his planetary model where the electrons are traveling in orbits like planets around the sun. And finally, the modern model, which I don't know where that is. Hold on, maybe the next page. Nope, it's not on the next page. But these notes are available to you, so I would suggest you look them over. Okay, so the first scientist that we're going to talk about is Dalton. And Dalton's discovery was around 1808 when he came up with his 4 major postulates. And these postulates led us to the modern atomic theory that we believe today, and it was a starting point. He came up with 4 basic statements about the atom. The first statement was all matter is composed of indivisible particles called atoms. The word indivisible means you cannot divide it any further. Well, in today's modern theory, we know that the atom is in fact divisible. We can divide it into 3 smaller major components. We call them subatomic particles, 3 subatomic particles, major subatomic particles of the atom: the proton, the neutron, and the electron. So although Dalton's statement, all matter is composed of indivisible particles called atoms, was very profound at the time, it doesn't really hold true today. It was just a starting point. He also said all atoms of a given element are identical in mass and properties. Well, all carbon atoms have similar properties, that is true, but not all carbon atoms may have the same mass. When we talk about atoms having different masses, we call those isotopes. Isotopes are atoms with the same number of protons, but different numbers of neutrons. So therefore, they have different masses. And we'll talk about that in another video. The third thing that Dalton said was that compounds are formed by a combination of 2 or more atoms. This particular statement holds true today. You must know that in order for something to be considered a compound, it has to be 2 or more elements chemically combined. And finally, Dalton proposed that atoms cannot be created, they cannot be destroyed, they cannot be converted into any other kinds of atoms during a chemical reaction. Chemical reactions simply just rearrange the atoms to make new compounds. We are not creating, we are not destroying, and we are not converting anything. We are just simply rearranging them. The next scientist on our journey through the evolution of atomic theory is J.J. Thomson. J.J. Thomson discovered the subatomic particle called the electron by using a piece of equipment called a cathode ray tube. And he noticed when this subatomic particle went through the cathode ray tube that it deflected, which meant it bent towards the positive side of the electrode in the cathode ray tube. So he knew that this subatomic particle must be a negatively charged particle, and this negatively charged particle had to be embedded within the atom. Now, he didn't know that the negatively charged particles, where they exactly were. So what he proposed was that there were a positively charged area with negatively charged particles embedded within it. And those negatively charged particles he said were like raisins in plum pudding. So this model started to be called the plum pudding model, where the negatively charged particles that he just discovered were embedded like raisins in a pudding. A couple years after J.J. Thomson finished his research, along came a very, very, very important scientist that you must know. And this was Big Ernest Rutherford. I refer to him as Big Ernie. And Big Ernie did an experiment that you must commit to memory. It's called the gold foil experiment. In this experiment, Ernest Rutherford took a stream of alpha particles. Alpha particles were these positively charged particles, not protons, but essentially an helium nucleus, and he took these alpha particles, and basically these alpha particles were pointed at a thin piece of gold foil. And what he expected was that these particles, these alpha particles, were going to go straight through the foil. However, the alpha particles, most of them went straight through, but a few of them bounced back. And he exclaimed, it was like firing a cannonball at a piece of tissue paper, and the cannonball came back and hit you. And he had to hypothesize why that could be happening. So what he said was, if there was nothing there, then the alpha particle should be going straight through. And the alpha particle went straight through. He said that the atom had to be mostly empty space. Very important. The atom was mostly made out of empty space. However, the 1 out of 1,000 times where the alpha particle bounced straight back and reflected so that he could see that it was bouncing straight back, then he said it must be hitting something that was dense and hard and positively charged. So he hypothesized that there was a dense positive core to the atom, and he called this dense positive core the nucleus. Very important. Make a mental note. When you're talking about Ernest Rutherford's or Big Ernie's gold foil experiment, you want to commit to memory that the atom is mostly empty space and that it has a dense, positively charged nucleus. Here we have a picture of Ernest Rutherford's gold foil experiment. You can see that there was a box, and in the box he had a radioactive substance, and that radioactive substance was giving off the alpha particles. Remember, the alpha particles were the helium nuclei, and as those helium nuclei flew out of the box, there was a little bit of a slit in the box so that the particle would only come out in one spot. He aimed it towards the gold foil, and most of them went straight through and hit way back here. Okay? However, some of them reflected straight back or to the side over here, and that meant that they were coming close to something that was also positive and dense. It was almost like two billiard balls that were hitting each other. When the billiard ball hit, it flung right back. When it didn't hit and it went straight through, it hit the reflective surface up here so you could see that it was hitting straight through. The next scientist that we have to talk about is Niels Bohr. And Niels Bohr came up with the planetary model of the atom. And you'll notice that this is all happening rather quickly. Within, 15, 20, 25 years, we've gone from a plum pudding model with J.J. Thomson to Ernest Rutherford, Big Ernie, talking about a hard, dense, positively charged center. And now we have Niels Bohr, who said, okay, well, if the positively charged substances, the protons, are located in the nucleus, which is in the center of the atom, then the electrons have to be traveling in orbits around the nucleus. And these orbits each have their own particular energy level. That was his contribution. He said that these electrons were in specific energy levels, and as you got further away from the nucleus, you got more and more energy in your electrons. So when you look at this model, maybe if I can make it bigger. Ooh. I don't know how to make it go to the front. Alright, we'll get there someday, guys. Alright, so we have, in the center we have a nucleus, and then you have these rings. This is the first ring, this is the second ring. In the first ring can hold a maximum of 2 electrons, and those 2 electrons have the lowest amount of energy. Then in the second ring out from the nucleus, you have a maximum of 8 electrons, and those 8 electrons can have more energy than the 2 electrons in the inner ring. And then they get more and more energy as you go further and further out from the nucleus. Now these electrons can jump energy levels. When you put energy in, like we light it on fire or we give it a flame so that you're putting energy into the atom, the electrons can jump to higher energy levels. And when these electrons jump to higher energy levels, we say that the electrons are in the excited state. Now they can't stay there. Just like if I lit your butt on fire, if I lit you on fire, you would jump up, but you can't stay up in the air. So these electrons will then fall down to what we call ground state, when they release energy. So as your tushy is getting lit on fire if I put a match under your tushy and you jumped up, you putting energy in, the electron jumps up. When you go, ah, that's energy being released in the form of sound, because energy can be sound, and then the electron falls back down to ground state, and you would fall back down into your chair. Now, nobody should be lighting anyone's tushy on fire, but that's the way it happens with electrons. When the electron gets more energy, it jumps up, and then as the electron falls back down to the ground, it emits that energy that you put in the form of light. And that light is characteristic of the particular element that we're talking about. If we were talking about copper, if you've ever seen a green flame, if you had a fire and you threw some copper salt in there, you would get a beautiful green flame. They sell those at some of the fireplace stores, and you see this beautiful green flame. Well, that's essentially what you've done. You've taken the copper, you've excited the electrons, they jumped up to higher energy levels, and then the electrons fell back down, and instead of screaming, ah, they emitted that energy in the form of light. And the light happened to be green for copper. And for lithium, it would be red. For sodium, it would be yellow. Each particular element would have its own specific color of light. Okay, so the last stop on the evolution of the atomic theory is the wave mechanical model, and that's the model that we have today. I have this picture here. In this picture, it's a little bit above what we need to know, but you can see all these lovely little shapes. There's this round shape, and then there's these little, I don't know what you would call them, hourglass shapes, and then you get some more funky shapes down here. In this particular model, it's different than the Bohr model because the electrons are not traveling in orbits. They are in orbitals. And there's a difference between an orbit and an orbital. An orbit is a single path around the nucleus, where an orbital is a three-dimensional space. Again, I haven't really figured out how to get these things to not overlap. Here, let's move that out of the way. So if you look at this picture right here, you've got a dense region close to the nucleus. The nucleus would be right there in the center. And then you've got a dense region, and then it gets less and less dense as you go out. Well, this region is a three-dimensional region, and, hey, it shows where you're most likely to find an electron. So these shapes right here, this S shape and these P shapes, Px, Py, Pz, for those of you who understand the coordinates from math, the x is the horizontal axis, the y is the vertical, and the z is front to back. And that's what that's referring to. It's showing you the areas around the nucleus. The nucleus would be right here in the center. Let's see if I can get my pointer right there. Right there in the center. Right there. So it's showing you the region in which you would most likely find an electron. Orbitals are the region in which you're most likely to find an electron. In today's model, which is called the wave mechanical model or the modern present-day model, we have orbitals, and those are areas of high probability for finding an electron, not circular paths. Okay? And many scientists have contributed to this theory, but it's not important that we memorize their names. We just have to know how the evolution of the atom progressed from Dalton, who said they were hard, indivisible spheres, which we know is not true, through J.J. Thomson and his discovery of the electron with the cathode ray tube, and then we had Ernest Rutherford, who did the gold foil experiment, who told us that the atom was mostly empty space, but it had a hard, dense, positively charged nucleus. And then we had the Bohr model, where the nucleus was in the center and you had all the rings of electrons around it, and that's the way we're going to draw them most of the time this year. And then finally we have our wave mechanical model, which shows the electrons in orbitals around the nucleus. I hope that helped. I'll see you next time.